All right, so in 10.1 and 10.2, what we're going to take a look at is solving systems. As I mentioned before, we're going to use two methods today that you've done before, elimination and substitution. We might do one with graphing. We're not going to spend a ton of time on it because we've done graphing before. You put something in y1, put something in y2, second calc intersect, and that's it. So we're going to focus mainly on algebra. And the types of problems that we're going to be solving are all going to have at least two variables. Okay? In order to have a system, you have to have two variables. And in general, you don't always have to have the same number of equations as you do variables, but then weird things can start to happen. So we will always have as many equations as there are variables. So in a problem like this, two variables, two equations. In a problem like, let's say, this one, three variables, so I'll give you three equations. And that's really as high as we're going to go with elimination and substitution. If you want to go beyond that, then what we're going to learn tomorrow is more useful. Okay, if you have to do 4 or 5 variables. So for this first one, we're not going to solve it. We're just going to set it up. And it's asking us to find two things, the length and the width of a rectangle. So since it's going to have two variables, how many equations do you think we're going to have to set up? 2. Yep, we're going to need 2. So that means they're going to have to give us 2 facts about this rectangle that we can change into an equation. So the 2 things that they tell us, the perimeter is 100 and the area is 300. So let's start just writing down those 2 formulas. You don't even have to put numbers in it yet. What's the formula for the area of a rectangle? John?
It's length times width, so L times V.
So the area is length times width. And what about the formula for the perimeter of a rectangle?
No, 2L.
2L plus 2W. Okay. And we're using L and W, but a lot of times if you're solving a system with 2 variables, X and Y, is probably the most common letters you would see. But L and W works good here because it represents the length and the width. All right. So let's fill in what we can in that first equation. If I do that, Maddie, if I fill in what I can for A equals L times W, what will it look like?
300 equals L times W.
Okay, so 300 equals L times W. That's all we're going to be able to do there. And Madison, what about if I fill in for the second equation?
100 equals 2L plus 2W.
So, yep, 100 equals 2L plus 2W. So there's the 2 equations you would set up. Again, we're just setting it up. So I'm going to explain one of the methods that you can use to solve a system, and then we'll go ahead and try it on this one. Questions on that? Okay. So the 2 methods that we're going to look at are substitution and elimination. This problem is really set up more to use one of them over the other one. And it's really set up to use substitution. Okay, elimination is good when you have 2 equations that have the exact same kind of format to them. Like if you look at these 2, you've got x's in one column, y's in another, constants in another. So you could use elimination to solve this one. But when you have 2 equations and they look different, like you can see on the right one, you got L's in a column, W's in a column, then constants. But then on this one, you have a product. So this format doesn't match this one. So because of that, you're going to use substitution. So there's really three steps to use substitution. First, you really have 4 choices when you're doing a 2-variable system. The first choice is pick an equation. So you can pick like the top one or the bottom one. Once you pick an equation, then you have a choice of what variable you want to pick. And there's 2. So you can pick the x variable or the y variable. Or in our case, it's the L or the W. So you pick an equation, and then in that equation, pick a variable to solve for. In general, you want to pick an equation where you can try to do as little work as possible to get a variable by itself. So if I was going to pick one of these 2 equations to solve for x or y, which one do you think I would pick? Yeah, the second one. Because I can get x or y by itself. That doesn't really matter in one step. If you want to get x or y by itself in the top one, you're going to have to do at least 2 steps. And you're going to end up with a division step. And anytime you divide, you could end up with fractions. So we don't have to divide by a number. We're going to try to avoid fractions if we can. So you pick an equation, solve it for a variable. And once you do that, you're going to take what you did in step 1 and you're going to plug it into the other equation. Once you finish step 2, you're going to have a variable, you're going to have an answer. Okay? You're going to know one of your variables at this point. Always remember though, when you're solving for a system, you have to solve for every variable. So if you only solve for one, you're only half done. So once you get the answer for your variable that you chose to do in step 2, you're going to take that and you're going to plug that answer back in. Where do you plug it back in? It doesn't matter. Just plug it into one of the original problems, one of the original equations. I try to pick the one that looks easier. And then once you do that, you'll know your other variable. Now, if you're doing substitution, you have to do this a couple more times. Usually then, at this step, now you know 2 variables. Then you have to plug those 2 back into another equation to get the 3rd variable. So you just have to continue that. But any questions on those steps? Okay, let's try substitution on this one. So Sophie said we should solve the bottom one. I think that's a good idea. And what letter do you want to get by itself in the bottom? X? Okay. So I'm just going to put an arrow here. X equals. And what would go in that box? 300 over y. Right, so that's step 1. Pick an equation. We pick the bottom one, solve it for a variable. We did that. Now, plug that into the other equation. Where are we going to fill in 300 over y? For what letter in the top?
X.
X. So we're going to replace x with 300 over y. And if you do this right, you should only have one variable in the whole equation. So we're going to have 2y plus 2 times, so we're going to double this fraction. When you double that fraction, you get 600 over y. So 600 over y equals 100. Now, solve for x. Solve for y. Okay. What should we do first there? Solve for y. Guess what we should do? John?
Divide by 2.
Divide by 2?
What's that?
Okay, so what do you get if you divide everything by 2?
Divide everything by 2. Is it y plus 300 over 25y?
2. It's just
If you
y.
divide by 2. Oh, 2y. No?
It's just y, right?
Just y.
Just y. Okay. Oh, it is equal to 50.
Okay, not necessarily what I would have done first. Dividing by 2 was going to come up in this problem at some point, so it's fine, we did it now. We would have had to do it later. But we still have to deal with something else I was thinking of first.
Multiply by y.
Yeah, we got to get rid of that fraction, so we do need to multiply everything by 1. Right. And when I do that, now I have y squared plus 300 equals 50y. So what kind of equation do we have to solve now? It's a quadratic. So anytime we want to solve a quadratic, we want to get it equal to what? We want to get it equal to 0. If you had divided by 2, I would now at this step say, get it equal to 0 and divide it by 2. But we already divided by 2, so that's fine. So y squared minus 50y plus 300 equals 0. What's one way you can solve a quadratic if the numbers work out nice? If the numbers work out just right, you can try to factor it. I don't know if you're going to find two numbers that multiply to give you 300 and subtract to give you 50, or add to give you 50. I don't think so. So what's our other option if we can't factor it? Quadratic formula. So let's set it up to solve the quadratic formula. So we got negative b plus or minus the square root of b squared. We're going to know very quickly if we could have factored it, because if the square root comes out to a nice number, then it probably was factorable. If it doesn't, then it wasn't. All right, negative b squared minus 4ac all over 2a. What do I get under the square root when I simplify that?
750.
1300.
So yeah, 1300. And the square root of 1300 is not a nice number, so no, this would not have been factorable. Okay, let's type those in and see what we get. And remember, we're going to get two answers now, just for the y. We still have to go back and find x. But once you know y, that's easy. Just take 300 divided by y, and that's x. All right, let's write down our two answers for y. At this point, I am going to round everything off. It was an exact answer up until now. And we'll round to 3 decimal places. So we get 50 plus the square root of 1300 and divide by 2 gives me 43.028. And now do the same thing, except do 50 minus the square root of 1300. And divide that by 2. And we get 6.972. Okay. So there's our first two values, y1 and y2. Now we need x1 and x2. And remember, we're solving a system, so we have to go back and find the other two. What did I say we have to do with the y value to get the x value? You just plug it back in right here. 300 divided by the y value gives you the x value. So let's take 300 and divide by the y value. 43.028. 6.972. Anyone have a guess what x2 is going to be?
43.028.
Yeah, we're pretty close to it if we rounded, so it might be 0.029 or something, but it should be about 43.028. Because remember where these numbers came from. This was really the perimeter and area problem. I just changed the variables to x's and y's. So what it's basically saying is there are two rectangles that satisfy the problem where the perimeter was a certain number and the area was a certain number. You can have a rectangle that's like this, Or you can have a rectangle that's like this. And they're congruent. But they're basically the same thing. But if you think about these as ordered pairs, these are definitely different answers. Graphing the point 43, comma 6 is different than graphing 6, comma 43. Right, so those would be both your answers. Any questions on that? So definitely a more advanced two-variable system. Certainly in Algebra 1, you wouldn't start out with a quadratic equation. And not every problem will be a quadratic. This one is not. Okay, this is a much simpler, probably more Algebra 1 type of system. Beginning of Algebra 1. Okay, so 2x plus y equals 5, and 3x plus 2y equals 2. Now we're still going to stick with substitution. We are going to do elimination, and this would be a good one you could do elimination on. But let's try substitution one more time. Okay, which equation should I solve for a variable? Top or bottom?
Top.
Which one?
Top.
Top? Okay, let's go with the top. And which variable should we solve for? Y. If you can find a variable that has a coefficient of 1, that's the easiest one to get by itself. Can someone tell me what y would equal? Yeah, it doesn't have to be in y equals mx plus b form. That's really what we're doing here. But if you write 5 minus 2x, that's fine. In Algebra 1, I would encourage negative 2x plus 5, so they get used to slope intercept, but we're not doing that. Okay, so we got 5 minus 2x. What do we want to do with that now? 4? Y. Take that, fill it in. And anything we want to be careful about when we're actually writing it out, when we plug that in, something I usually make sure I put when I'm writing the problem out, especially because of what's going to happen here. Yeah, I really need parentheses because this is 2 times everything you fill in for y. So that's a distributive. So 3x plus 2 times 5 minus 2x equals 2. All right. Nick, can you distribute that out for me? And yeah, go ahead, just distribute it out.
3x plus 10 minus 4x.
Minus 4x. All right, combine your like terms. Let's see, we have a 3x minus 4x, so negative x. And let's move the 10 to the other side. What's going to be on the other side? Negative 8. So x equals how much?
8.
8. And that is the only answer. It's not a quadratic, so you don't have to get 2 answers for x, just 1. Any question on how we got x? Okay, what do I have to do now?
Plug it back in.
Plug it back in. Plug x back in, and then we'll solve for y. Okay, so I'll do that. You know what, I'll just do it right here. 5 minus, what's 2 times 8? 16. 16. And 5 minus 16 gives me negative 11. Now, if you want to check, you can plug it back in and see. So 2 times 8 is 16. 16 plus negative 11, that's 16 minus 11. Yep, that's 5. And 3 times 8 is 24. 2 times negative 11 is negative 22. So we've got 24 minus 22 equals 2. So we know we did it right. So you might have a problem where all you have to do is check an answer. Like I'll tell you, I'll give you a coordinate and I'll say, is this a solution? So you just have to plug it in and check it. All right, now if we were to solve each one of these equations for y, I kind of already said this, and graph it, what would each of these equations look like on a graph? They're not quadratic, so they're not going to look like parabolas. They would each look like a line. And what would happen on the graph at the point 8, negative 11? That's where they would intersect. Right? So you can always double check something by graphing it and seeing an intercept. Or if you're using technology, I wouldn't do that if you're using graph paper by hand, especially because your answers could come out to decimals. So this last problem would not be a good problem to solve by graphing. This one would be okay. All right, so substitution is one way. Not the most efficient way if you're going to get into 3 variable problems. Substitution can get kind of cumbersome just to deal with. So elimination is another way. And the idea with elimination is you look at your equations and they have to have the same format. Like x is in a column, y is in a column, constants in a column. And what you do is you try to get the coefficients of one of the variables to be opposites. You could do the same, but let's just say opposites. If you do opposites, then you can add them. If you do the same, then you'd have to subtract them. We'll just do opposites. And a linear combination is when you multiply an equation through by a number. So like x plus 2y equals 5. Well, if I multiply that by 10, I get 10x plus 20y equals 50. The second thing I said is a linear combination of the first one, because it was multiplied through by a number. So sometimes you have to multiply, well, if you're really lucky, you might have 2 equations where one of them has like something like this. And when you go to add these up, they already have a number that's opposite. So elimination is perfect because the x's will be gone when you add. Now, sometimes it doesn't work out quite that nice. And in this case, you'd have to multiply the top equation by a number. And if you do that, you could make this and this opposites pretty easily. You could make 8 and 3 opposites, but if you decide to do it that way, you're going to have to multiply the top and the bottom by a number. So if you can avoid multiplying both equations by a number, try to do that. If you can't, then you're going to have to multiply both. And it's all about looking for the LCM. Try to find the least common multiple between your coefficients. So as I said, it might be necessary to multiply one equation by a number, or you might have to multiply both. All right, so looking at this one, and assuming we're not going to multiply by fractions, because that gets kind of messy, do you think we're going to multiply one equation by a number, or both? Yeah, we are going to have to do both. And what coefficients do you think we should make opposite? The x ones or the y ones? Yeah, I would do the x's. Because one thing the x's already have going is they're already, one's a positive, one's a negative. So we already have that part. So what could we multiply with, or actually, no, let's think of it this way. What's the least common multiple between 2 and 3? 6. So that's going to be the goal here. You want to have one of the x's be a 6, and you want the other one to be a negative 6. What could you multiply the top equation by to make that happen? 3. And so now we've made the top equation a 6 in front of x. So you want the bottom equation to be a negative 6. So what could you multiply the bottom by? 2. So remember, that's a distributive property to everything. So let's do that out and see what we get. Michael, if I distribute 3 to that top equation, can you tell me what I get?
6x plus 9y equals 15.
Okay. And Leanne, if I distribute 2 to the bottom equation, what do I get?
Negative 6x plus 10y equals 42.
Okay. Now, because the x's are opposites, add them up. So John, what do I get when I add the x's?
0.
Gone. Madison, when I add the y's? 19y. Sophie, when I add the constants? 57. Divide each side by 19. And what do I get? Maddie, what do I get for y?
Y equals 57 over 19.
Mm-hmm. What does that simplify to?
Three.
3. Right? So 19 goes into 57 exactly 3. Now, from here, the end of this problem is just like substitution. Plug it back in. The only downside is you don't have an equation where x is already by itself. With substitution, you would. So we're just going to pick an equation and plug y in. Which one should we pick? Yeah, the top one, the numbers are a little smaller in general. So take this, fill it back in for y. So 2x plus 9 equals 5. 2x is going to equal how much? -4. So x is -2. So there could be two ways I set this up on the test. Either I give you a single box and you type a coordinate in it, like -2, 3. Or I'll give you two separate boxes and you put the 2 or the -2 in one of them, put the 3 in the other. Any question on that? So that's an elimination where we solve, get one answer for x, one answer for y. Again, if we were to graph these two equations, and you've got y by itself, they would both be lines, and that's the coordinate where they would cross. Now, let's think a little bit more about lines. If you're drawing two lines, you could have what happens here, which means you draw them and they cross in exactly one spot. So they make an X shape. What else could happen if you draw two lines?
They could be parallel.
They what?
They could be parallel.
They could be parallel, which would mean, what would the solution be?
No.
That would be a no solution. So you can get a one solution, that's where you draw the lines and they cross. A no solution, where you draw the lines and they're parallel. One more thing that could happen. Yeah?
The same.
Right, it could be the same line, so how many solutions would that be? Infinite. So you draw one line, you draw the other line, and they're the same thing. So let's try an example where one of these special cases ends up happening. All right, so 2x minus 3y equals 5, and -6x plus 9y equals 10. Okay, so let's do elimination because I think that's the easiest way to get rid of a variable. What coefficients do we want to make opposites? X's. Okay, what's the least common multiple of 2 and 6? 6. Since the bottom one already has a 6, you don't have to do anything to it. I'm just going to copy it over. You don't have to do this. I'm just doing it over here so I have room to do my work. So if the bottom one is a -6, we want the top one to be +6. How do we make that happen? By what? By 3. So that's going to give me 6x minus 9y equals 15. Okay, when I add up my x's, what happens?
0.
Gone. My y's?
0.
Gone. My constants? So I get 0 equals 25. Whenever all the variables disappear, it's now a special case. What do you think that means in terms of the solution?
No solution.
There's no solution. When you end up with a false statement, there is no solution. That means if you were to get these equations with y by itself and you graph them, they're parallel lines. They would never cross. They have the same slope, but they have different y-intercepts. Okay? So that's a special case. Let's try this one. All right, what coefficients do we want to try to get the same this time? The y's? Okay. What's the least common multiple between 3 and 6? 6. So the bottom one can stay the same. Well, the bottom one has a 6. We want the top to have a negative 6. So what would you multiply by? 2. And what do you get when you multiply by 2? 2x. What'd you say? Minus 6y. Negative 4. And when you add the x's, what happens? How about the y's?
0.
0. How about the constants?
0.
So I end up with 0 on the left and 0 on the right. All the variables are gone, so it is a special case. What do you think the answer is this time?
Same line.
It's the same line. These are the exact same equation, one right on top of the other. So there's an infinite amount of solutions. Any questions on that? All right, so I hope most of this so far seems pretty, straightforward stuff you've done before. Getting into 3 variables is a little tricky sometimes because you have more options. It's like, well, which equation do you want to pick? You've got 3 choices, and now you have 3 variables. So the idea of what we're going to try to do is we're going to use elimination. We're not going to use substitution except at the end to plug our answers back in. But we're going to pick a variable to eliminate in 2 of the equations. In general, try to pick an equation that has a variable with a coefficient of 1. So if I see something that has a coefficient of 1, that's probably one of the equations I'm going to use. And I'm going to try to eliminate the x in the other 2 equations by using a linear combination of this. I don't know what's going to happen with the y and the z's. I'm not worried about that. If one of those cancels at the same time, that's great. If it doesn't, that's okay too. But we're going to pick a variable to eliminate in 2 of the other equations. Then what you're going to do after you do that is you're going to take your problem that originally started with 3 equations and 3 variables, and after you do this step, you're going to be down to 2 equations and 2 variables. Now you can solve that just like we've been doing. Solve for one of the variables in those 2. So you're going to do elimination again. Once you eliminate the variable again, you're going to be down to a single equation with a single variable, and then you're going to solve for it. Then you're going to use substitution and work backwards to get all your other variables. It's still a little confusing maybe when I explain it, but I think when you see it, it'll make more sense. So let's try. So there's going to be a lot of copying over. So as I copy things, make sure if you see a mistake, let me know. Just to make it simple in terms of talking about equations, I'm going to call this equation 1, equation 2, and equation 3. Anytime I put a number in circle, that represents an equation. It doesn't represent like arithmetic. Okay. All right, so do we have an equation here that has a single positive variable?
Equation 3.
Equation 3. So we're going to use equation 3 twice. We're going to use it to eliminate the x in equation 1, And then we're going to use it to eliminate the x in equation 2. And once we do that, we're only going to have 2 variables and 2 equations left. Let's start by using 1 and 3. I'm going to copy these down so I don't have to keep scrolling up. 2x plus 3y minus z equals -1. And x plus 4y minus 3z equals -8. Now, what letter did we just say we were going to try to eliminate? X. So, if you want to eliminate x, what's the least common multiple between 1 and 2? Yeah? 2. So we're going to keep the top equation the same. 2x plus 3y minus z equals -1. I end up doing a lot of copying over. Maybe you want to try writing it a little differently, but I'm trying to show you every step. Okay. And what would I multiply the bottom by to make the x value in the bottom the opposite of the one in the top? John? -2. And can you tell me what I get when I distribute that out?
-2 minus 8y.
-2 minus 8y.
Plus 6z. Is equal to 16.
Anything else? I think I wrote everything you said, but I don't think you said something.
Oh, did I not say the x?
I don't think so.
Oh.
So yeah, -2x minus 8y. Just double check it, make sure it looks good. Right? And now this is going to give us a 2-variable equation. It'll give us 1. We still need 1 more. So those are gone. Madison, what do I get for my y's? -5y. Sophie, my z's? Plus 5z. And Maddie, my constant? 15. Now this normally doesn't happen, but there is something you can do here to make this equation a little simpler. And it's just because of the way everything worked out. We can divide everything by 5. You don't have to, and most times you probably won't have a number that's a common divisor. But in this case we do. So let's say -y plus z equals 3. I'm going to put a box around it, and I'm going to call that equation 4. So I just created an equation that only has 2 variables based on this system. Now I need 1 more equation. I created that using 1 and 3. So I can't use 1 and 3 again. Let's use 2 and 3 and create another equation. I'm sticking with 3 all the time because it has a 1. That's why I'm using it. All right, so now let's do the same thing, except we're going to use 2 and 3. And the goal is when we get equation 5, we're going to use that one with equation 4 to get rid of the y or the z, whichever one we think is easier. So equation 2, 3x minus 2y plus 2z equals 15. And equation 3 is x plus 4y minus 3z equals -8. Now, at this point, you're kind of locked in. You already got rid of x in this one. You have to get rid of x in this next one. It's the only way this is going to work. So, what's the least common multiple between 1 and 3? 3. So, we're going to leave the top one the same. It already has a 3. 3x minus 2y plus 2z equals 15. And what are we going to multiply the bottom one by? -3. And when I do that, John, what do I get?
-3x minus 12y minus 19 is
All right, you said negative 3x minus 12y. What's the next one?
Minus 9z. Or sorry, positive 9z plus
Yep. Unfortunately, one mistake in this whole process, and then it's all messed up. So plus 9z, and what'd you say the last one is?
negative 24. Or positive 24.
No, positive 24. Okay, so add those up, and that's going to give us another equation. These are gone. Annalise, what do I get for my y's?
10y or are you adding them or subtracting them?
Add it.
Negative 14.
Yep.
Y.
So negative 14y. Nick, my z's.
11z.
11z. And my constant, Ann? 39. Right, let's double check. I mean, I don't really like those numbers. Those are kind of, some of them are kind of big. I don't know, but I don't think we did anything wrong. I know all the answers come out nice, so if it doesn't, then we know we made a mistake. Okay, so now that is equation 5. Now, you want to use equations 4 and 5. And from here, you can do what we learned earlier. Solve for y or z. Let's write them both down. So we've got negative y plus z equals 3. And negative 14y plus 11z equals 39. Let's see, so do we want to get y? Do we want to eliminate y or z? Yeah.
Z.
Okay, what's the least common multiple between 1 and 11?
11.
11. So we're going to copy this one. And what are we going to multiply the top one by?
Negative 11.
Yep. So multiply the top by negative 11. That's going to give you positive 11y minus 11z equals negative 33. Okay. John, when I add my y's, what do I get?
3y. Or negative 3y.
Negative 3y. And Madison, my z's? They're gone. And Sophie, my constants? 6. So Maddie, that means y equals how much?
Negative 2.
Negative 2. Now from here, even though we only have one answer, we're like 90% done the problem. Because it's going to be very easy now to start to fill back in and get the other ones. Next, I would use the equation negative y plus z equals 3. So negative y plus z equals 3. When I fill in negative 2, I'm going to get negative 2 plus z equals 3. 2 plus z equals 3. There's your second answer. Okay, so we got z, we've got y. The only thing left to find is x. And now you just plug y and z back into either original problem. I would pick equation 3 only because you're solving for x and you don't want x to have a coefficient in front of it. So if we do that, we already have one step done. So x plus 4y minus 3z. Is it equal to? Negative. All right, x we don't know. What's 4 times y? And what's negative 3 times 1? Negative 3. Negative 8 minus 3 is how much? So that means x equals how much?
9.
Yeah, 3. There you go. So it's a little bit more work with the 3 variable and 3 equation, but it's still the same idea. Any questions on that? Now, if you notice, we had to do lots of writing. And letters make up, maybe not quite half of what we had to write, but I would say letters make up at least 30 to 40% of everything you just wrote down. Lots of letters. Instead of writing a problem like this, we could represent this whole original problem like this. How am I getting what I'm writing right now? What am I doing?
Taking the coefficient.
Yeah, all I'm doing is writing the coefficients. I'm eliminating having to write the equal sign, and I'm eliminating all the x's, all the y's, and all the z's. So right away I cut out 3, 6, 9, 12 different symbols I had to write down, and it still captures the same information. This is called a matrix. And a matrix is just a more efficient way to organize information about a system. So if you want to write this one in a matrix, 1, 2, 3, 1, 4, negative 10. I mean, that cut way down on the amount of stuff I had to write. And tomorrow, we're going to talk about using elimination in a matrix. It's a little bit different than the sequence we did today, but it still accomplishes the same goal of figuring out your variables. Right? So we'll talk more about matrices tomorrow. And this is a method that really scales to if you have to solve 4, 5, 6, even 20 variables. You can do it in a matrix a lot easier than trying to do elimination by hand. Because you can also use the calculator to help you, a graphing calculator with matrices. We don't really get into that because we don't do a big enough matrix that it would be worthwhile, but you could. All right, so that's the homework for tonight. We've got a little over 20, maybe 25 minutes or so. So you've got a little bit of time, you could start that. If you need to check in with me about grades, making anything up, now would also be a good time to do that.